Other classification methods include support vector machines, which finds optimal boundaries between categories, decision trees, which makes classification through a series of yes or no questions, ensemble methods, which combines multiple classifiers for better performance, and neural networks using deep learning approaches. Now, regression, on the other hand, is used when the output is a continuous number. What's the probability of default? So instead of asking if a customer will default yes or no, you're asking what's the probability given customer will default. Or, for example, if you're asking what's the expected loss if this loan defaults, again, the answer is a continuous number. Or what's the interest rate a given customer should receive. The output in all these cases is a numerical value on a continuous scale. Regression algorithms include linear regression, which I'm sure you're all familiar with, which fits a straight line through the data. GLM, which stands for generalized linear methods, extends linear regression to non-normal distributions. And Gaussian process, which is a flexible probabilistic approach to regression. So then the key difference between classification and regression problems is that classification answers which category, while regression answers how much or what value. In risk management, we use both extensively. We use classification to identify fraudulent transactions. So in that case, the categories are fraud or no fraud. To determine credit rating categories, so AAA, AA, A, BBB, so these are all ratings for bonds. To identify high-risk transactions that need additional review. We also use regression to estimate the probability of default, to predict loss severity, to forecast risk levels, and to estimate exposure amounts. Now let's shift to a fundamentally different approach, which is unsupervised machine learning. So in this case, we don't have labeled data, as you can see, because we say unsupervised. So in unsupervised learning, the situation is reversed. The machine is trained using an unlabeled data set. So essentially data where we don't know the correct answers to. We don't have labels. We don't know the right answer in advance. The machine is enabled to predict the output without any supervision. It has to figure out the pattern on its own. So here's the key. An unsupervised learning algorithm essentially tries to group the unsorted data set based on the input's similarities, differences, and patterns. So the system looks at the raw data and asks, what natural groupings or patterns exist in this data? What can I learn about the structure of this information? This is very useful when you don't have labeled data. And the reason why this is common is because labeled data is expensive. To label data, you often need human experts to go through and classify examples. That's time-consuming and costly. So unsupervised learning lets you extract insights from data without having to label it. So let's see an example. Imagine a bank has millions of customers, all with accounts and years of transaction history, but they haven't classified which customers are high risk, medium risk, and low risk. So an unsupervised algorithm could examine the transaction pattern and automatically group customers into clusters or buckets based on their behavior. Maybe it discovers that customers with certain patterns, like frequent international transfers or people with sudden large withdrawals or transactions at weird hours, all of these fall or tend to cluster together, for example. The bank can then investigate whether this cluster represents money laundering activity or simply different customer segments with real needs. So unsupervised machine learning is broken into two categories. You have clustering algorithms, which essentially group similar data points together. And the most famous methods are k-means clustering, fuzzy c-means clustering, Gaussian mixture models, and so on. These are all clustering techniques. So essentially, they try to find natural groupings in data, and then it's up to you to determine what tag you're going to give to each group. So you split the customers into groups and then say, okay, so this is the customers. This looks like the group of customers who, the high net worth individuals. This is the group of customers with more high risk individual, and so on. On the other hand, association algorithms discover relationships between variables. For example, an association algorithm might discover that customers who do X often do Y. This could reveal patterns, like customers who suddenly change their transaction patterns often precede fraud events, for example. Or customers with these characteristics tend to have high default rates. Now, we can also discuss hybrid approaches, which are called semi-supervised machine learning. So semi-supervised learning has some features from supervised learning and some features from unsupervised learning. It's the best of both worlds in some ways and the compromises of both worlds in others. The key distinguishing feature of this hybrid approach is that it uses the combination of labeled and unlabeled dataset to train its algorithm. You have some data with labels, so the correct answer is already known in that case, and some data without labels. And we're going to use both of them. So why would we do this? Because labeled data is expensive, but unlabeled data is cheap. So for example, we might have sufficient resources to label 10,000 customer records, but you have 10 million total customer records. So semi-supervised learning lets you leverage all 10 million records while using your limited labeling budget wisely on the most important 10,000. So how does that work? The system first trains on the labeled data, which are the 10,000 records here. So learning the patterns associated with known outcomes. Then it applies what it learned to make predictions on the unlabeled data. But critically, the system also learns from the structure and patterns it discovers in the unlabeled data itself. So it refines its understanding based on both sources of information. So using both types of data sets, semi-supervised learning overcomes the drawbacks of supervised and unsupervised options. Supervised learning alone requires massive amounts of labeled data. Unsupervised learning alone can discover patterns but provides no way to validate what those patterns correspond to, right? Because it's up to us to give a tag to each cluster. Semi-supervised learning then can balance these limitations. In risk management, semi-supervised learning is valuable for a situation, for example, where we carefully reviewed and labeled 5,000 transactions as fraud or no fraud, but then we need to process 100,000 transactions daily. Okay, so we want to leverage our labeled example to help classify the unlabeled 95,000. Now for something quite different, which is reinforcement machine learning. So reinforcement learning is a feedback-based process. The system learns through interaction with its environment, receiving rewards for good actions and penalties for bad actions. So this is how it works. The AI component automatically understands its surrounding by essentially the hit and trial method. So essentially it's like you're trying to train a puppy, for example. Okay. So the system tries something first, tries some action, and then observes what happened. Okay. So it essentially learns whether that action was beneficial or harmful based on the reward it gets as a result of the action. And then it's going to adjust its future behavior accordingly. So concretely, the component is rewarded for each good action and penalized for every wrong move. So if the system takes an action that leads to a desired outcome, so for example, if you're training a system to trade the stock market and it takes an action in simulation that leads to profit, so that's the desired outcome, then it's going to receive a reward signal. And it's going to learn that this action is good. If it takes an action that leads to an undesired outcome, then it's going to receive a negative reward, which is a penalty. Over time, the system learns which action lead to rewards and which lead to penalties, and then will always try to maximize the reward function. So the reinforcement learning algorithm tries to maximize the rewards by taking sequences of good actions. So the system will develop what's called a strategy, or in machine learning we call it a policy, for what to do in a given situation in order to maximize the total reward over time. So here's another example. You're trying to teach a computer program to play chess. Now you can't label millions of positions in chess as good move or bad move, but you can set up a reinforcement learning algorithm that plays many games and learns which moves led to finally winning the game and which moves led to losing the game. And then the system will learn to maximize wins. So for every given board configuration, it will know what's the best action to take to maximize its wins. In risk management, reinforcement learning is less common than supervised or unsupervised learning because we don't really do classification with reinforcement learning. But it still has potential applications. So, for example, portfolio optimization systems could manage to manage risk to give you better risk adjustment return. A trading system, like I said, could learn which strategies maximize profit while staying within specific risk limits. Or a resource allocation system could learn how to deploy fraud investigators most effectively.